every food product need a good packaging for the transportation, for the carrying, to extend the shelf life, and etc. etc. But here we are, what we are doing, we are using agriculture byproduct, food waste or meat byproducts, and from that byproduct or waste, we are extracting biopolymers and we are generating biopolymeric films that is biodegradable, edible, and having multidisciplinary actions in the food packaging, food. Okay, so but what's the problem with the plastic films? For example, if I ask you, can anyone answer what's the problem with plastic? We are already having a very good barrier properties. Packaging, plastic packaging is very cheap and it's having good barrier properties. So what's the problem? The problem is non. That's the major concern. Okay, so this is the major concern because like in India, every year annually, like we are producing 9.4 million metric ton of plastic waste every year. That is like in the whole world is the second after China. Okay, so we are producing that much plastic, and in this whole plastic waste, this food packaging sector is contributing 43%. That is like around half of the plastic waste is generated by food packaging sectors. Okay, and after this what the introduction of this online, now if you see like why we are fighting here with this plastic what to say packaging. Okay, so at the same time, what we are doing, food industries are generating a lot of waste, that we say sometimes green waste or red waste. Okay, it's coming from meat industry, so it's having it can get spoiled, and it's give very favorable condition to microbes to grow, and that may uh, harm our harm our health also, because our health or animals who are roaming in the outside. Okay, so so we are protecting that also, because we are reducing that waste also, and at the same time we are reducing the plastic waste too. So what we are doing in our lab, our group basically works on the from the agricultural byproduct and as well as from the animal byproducts. For example, uh, we are using seeds or straws, the rice straws, and different biopolymers from this chitosan, like chitosan from the shrimp cell, crab cell, and gelatin from fish, and from pork skin. A lot of like from meat byproducts. Like generally, you see if you go to the chicken shop, they throw their skin, they throw the feathers, which is having a very good source of protein. Like you can take out this gelatin or keratin, and this type of like legs also they throw. And at the same time, you see that in the jackfruit, most of the places people eat this jackfruit seed, but here people in some places they don't eat, they throw it. And tamarind seed, they throw it. Lot of like almost like all the fruits people are throwing the seeds, which is having a good biopolymers in it. So what we are doing, we are extracting the biopolymers from those seeds and agricultural waste, you can say, or animal waste, and from those biopolymer we are making films. Okay, so now I will start how we are doing it actually. So for that, first of all, we need to extract biopolymer, that I already told you. But that can be done by just some chemical methods. That's very simple. Simple. You can find it in lot of literatures. And after that, how we are doing that? How we'll make that a film? So basically, for example, here, for example, I'm taking here. This is gelatin. Okay, these are all the biopolymers. Whatever we have now. For like this is casein, and this is chitosan lactate. This is gelatin. This is starch, and this is gum. Okay, and here also we have some synthetic biopolymers like polyvinyl alcohol, and this one is our pectin. Okay, like there are a lot of types of biopolymers available in the market, or you can extract by yourself also. And for that, after that, like we need one more thing, either plasticizer or cross linkers. What's a plasticizer? It's provides the mobility to chains, polymeric chains inside the matrix, so that your films should be flexible. It's not like you don't need it like a papad. Okay, it should be flexible at the same time. At the same time, it should have good tensile strength. It should not be tear apart very easily. At the same time, it should not be like very rigid. It should be having some extensibility, flexibility, and it should be like easy to handle. It should not get teared up easily. Okay, and after that, we are the cross linkers are more like a lot of types, like sorbitol. You can use citric acid. we have, but I'm not saying because of less space. And these are to bind the matrix to one polymer chain to with another biopolymer chains, or with the same type of biopolymeric chains to each other. Okay. And one more thing which is lacking this plastic packaging, it doesn't have any activity. Okay. It's not antimicrobial. If you pack a meat in a bag of plastic, you cannot say that it will prevent the microbial growth also. The microbes will grow, okay, because it does not have any antimicrobial property and antioxidant property. So for that, what we are doing, we can use like essential oils, like for example carboprol, apple seed carrier oil, and basil seed oil, spearmint or curcumin. And there are a lot of essential oils or bacterial compounds you can use. You can make pH sensitive films also, ammonia sensitive films also. You can make smart packaging also. So for an example, I'm going to demonstrate how we are doing it. So what we are doing is the solution casting method. So there are a lot of methods like compression molding and extrusion method, but here we are doing solution casting method. So for that, for example, I'm here taking, I've already weighted it 3 gram, okay, 3 gram of gelatin. I have taken gelatin as a biopolymer, okay. So take beaker, I'm gonna take some water, distilled water or deionized water, whatever you want to take. Okay. This is deionized water, and we are saying that we will take 3% of biopolymers. So we have to take like 97 gram of water. So I'm not going to weight it. I will just take 97 ml of water. Will pour this water in a beaker, and I will keep it on magnetic stirrer, and I will turn on the RPM. Okay. Now it will rotate the solution. Magnetic bead will rotate the solution. Now, first I'm not going to show this like what waiting period, because first we need it to get heated at the temperature of, like for example I'm setting 70 degrees Celsius. So that also varies from polymer to polymer. It depends on polymer, what the RPM you are taking, what the temperature you are taking. For example, I'm taking this gelatin. So sometimes we need to do hydrolyzation of the biopolymers. And what in that case what we do, we just put this biopolymer in water before putting on magnetic stirrer. After that, after half hour, we keep it on the magnetic stirrer and then we heat it. But in this case, we don't need it. Okay. So why I'm keeping 70 degree? Because it's a protein, and the protein denaturation temperature is around 80 degree. So if I'm keeping the protein here, and if the 80 degrees Celsius reaches here, so protein will get denatured. Sometimes it's useful, sometimes it's not. So you have to check that also. It's not like you can take randomly some gram of biopolymer and you can do it. You have to optimize it. You have to do it 30, 40 times. You have to spend months to get an optimize formulation. Okay. So for example, this is now heated for 70 degree on 70 degree, and it's rotating on around 500 rpm. Okay. Now I will add the biopolymer slowly. Why? Because if I'll directly pour this whole biopolymer, it may form lumps. Okay. You can put it like this, or you can slowly slide it down like this, so that the whole biopolymer get mixed uniformly. Now, when you are working with any novel polymer, for example, which is having very limited research, very limited literature, and you are not having too much data about it, so you may not be very sure that this plasticizer or this cross-linker is the best for them. So, for example, I'm using glycerol here as a plasticizer because I already know that the gelatin is able to form the cross-linking within the matrix. So I just want gelatin, because I'm working on the gelatin. So I know that the gelatin is very rigid. and it's having very good tensile strength, but it's very less flexible. So then what I have to do, I have to increase the mobility in the chain, polymeric chains. So I need to add some plasticizer. So I already weighted. See, it's a 30% of the weight of the biopolymer I have taken. For example, 3 gram I have taken to 30% of 3 gram weight. Okay. So that also you have to optimize. How we will decide that it's 30%. You have to check with like 20%, 30%, 40%, 50%. Then from that you do the mechanical testing, barrier testing, and physical testing. Then from that you select which percentage is giving the best film. Then you have to select that percentage only. For example, after heating it, it's getting mixed. I'm not showing because it's the next batch is also there. So after it's got heated up to 70 degrees Celsius for like half hour, then after half hour I will add this glycerol here. Then I will cover it using this petri dish, and after that we have to just wait for another 10 minutes. Then we have to cool it down before pouring the solution. For example, so we have to cool it down, then only we will pour on the petri dishes. And that too, we have to weigh the biopolymer we are pouring on it. Okay. For example, I generally pour 20 grams because I'm getting very good film on that, thin and having good mechanical properties. Okay. So you can pour 25 grams, 18 grams, or 30 grams depending on your biopolymers. Okay. So for example, now since we are already prepared one solution to show you. Okay, you can see this is very viscous. Okay. So for that, like, we start the characterization of the film from this stage. Okay. First we do the rheology of this, in which we see the viscosity, shear stress of the solution. Then we see the viscoelastic property, G prime and G double prime, in this like we say it frequency sweep test in this rheometry. Okay. And after that, how we do it, generally we put it in weighing balance and we tear it. Then we pour it slowly and let it spread by itself. Okay. Generally in 20 grams or 25 grams, the whole plate will be covered. And after this, we will just keep this one in hot air oven, and that one also we have to set on what temperature we want to dry and for what time. For example, we are drying in 45 degrees Celsius for 1 day, sometimes 12 hours, sometimes even 48 hours. So after drying, after 24 hours or 48 hours, whatever you are drying, you will get the films. Like for example, this. And if you are pouring the solution in big quantities, you have to make large volume of the solution. And after that, if you pour in the same ratio, for example, area to volume ratio, same ratio, so you will get visible. Okay. So that's how you can make the films. This film is made from the xyloglucin, that the tamarind, what you say in your language, we say imli, that seed of that tamarind. From that we have extracted the one biopolymer called xyloglucin, and that is only from that xyloglucin with glycerol, nothing else. So that's how you can prepare the film. Now, and after that you can do all the characterization like FTIR, XRD, DSC, mechanical testing, tensile strength, barrier property, water vapor barrier property, oxygen transmission, etc. UV barrier. Okay. So that's all about the film. Now I will show you how we're doing the coating. Okay. I will just put it back here. Go for the spraying method, that can come easily out of the nozzle. And if it's very viscous, you have to go with this dipping method only. For example, I'm taking this tomato. This is nothing, just dipping and taking out, so that you have to make sure that the whole area is dipped. Whole area of this tomato is dipped inside this biopolymeric solution. Okay. Now I can leave it here. Now, like after an hour, you will see it will become very shiny, and it will have a film covering the tomato. that will increase the shelf life because it will reduce the permeation of microbes, and if you remove the permeation of oxygen, that will increase its maturity, so it will be fresh for longer time. Okay. And sometimes to prevent more further, we use the essential oils, which is having antimicrobial property. So if its surface is having some antimicrobes or an environment is having some antimicrobe, that coating will not allow that microbes to grow inside and penetrate inside. Okay. So that will also increase the shelf life. And second one is wrapping. And you can dip it inside this, and you can keep it like this only. Similar way. There's nothing very much to explain. Okay. For this one, sometimes it gets sealed with this hot sealing machine. Sometimes it temperature it's getting sealed more better. Like this. Okay. So it's very evident that it can be sealed in this one and it can be wrapped. So is this the cost? Like generally this cost of this LDP or LLDP is around less than $1 per kg, but for the biopolymer it goes up to $7. To reducing the cost is the biggest challenge, because this plastic packaging industry is already having a very advanced setup, and it's very large scale industrial the setups also. So they are producing a lot, that's why it's very cheap, and this raw material is also very cheap. And but it's already evolving biopolymers. Maybe in future, very near future, it will get evolved and advanced machines will come and it will get automatically cheaper. And second one is the awareness. People should be aware that it's also very very big issue. So if anyone have any question, that's all about this. If anybody have a question, so you can ask now, right now. Yeah, yeah. That question always comes because I'm doing PhD only, isn't it? So that question always comes. But in yeah, yeah. So basically, like, it's the question of personal belief, ethics, and it's what to say, personal choice also. So even though some people who are eating, who are veg, but they don't care about the packaging. Okay. But in India nowadays, if you see, most of people are non-veg only. So we cannot concern with this minority for the application of majority. So if you see the whole world, the non-vegetarians are in the majority. So why should we concern over that? It's already a very big market. So if it's reducing more than half of the plastics, so why not? So whoever want to prefer, they can prefer. And in any case, like gelatin, it's not only gelatin. There are a lot of like you see that uh, uh, one is there, Dr. Janaswamy. Uh, he's in University of which South Dakota. South Dakota. He's making very good films, just like these films from the rice straw and rice husk, from this agriculture waste from the farms, and he's making very good films. That is acceptable for vegetarians or non-vegetarians. So we are doing our best from our end. They are doing their best from their ends. So like I have not. Uh, uh, mm, mm. It gets sticky. That also you can like counter it with your formulation. For example, if it is getting in like in different RH, for example higher RH, like above head 60%. So you have to play with your plasticizers. If you are using glycerol, you try some other like plasticizer or cross linkers that that can counter this issue. So because I have done like the same issue I was also facing at the beginning of my PhD, but later I reduce the concentration of glycerol, it got sorted out. I used the like PEG, citric acid, and this or sorbitol, but the glycerol reduction of glycerol was enough for me. See, in the case of coating, yes. So like that's why it's recommended like if you're getting coated like fruits, however it is edible, but still you should for your personal like sensory like appetite, you should wash it prior to eat. So yeah, migration is also very big issue, like migration of nanoparticles and migration of essential oils, and that is hampering this sensory analysis. That is also a very big issue. That like in the case of wrapping, it's okay, it's still okay, but in case of this coating, it cannot be avoided 100%. So that will be always be issue. That's in that case you can do like for example, I am doing in chicken. So what I have done, like I'm using curcumin, that is coming from turmeric, but most of the people are using turmeric for the marination of chicken. So that's not that much like questionable. So that thing we can do, like whatever go with this food, that we should use. Hmm. Smell will be there. Yeah, yeah, it can make. Yeah, that those are the challenges only that still exist. Oxygen OTR I haven't performed because we don't have the facility here. So I'm not sure. I cannot say with a certainty that this is the permeability because we don't have the facility. So any other questions? Yes, tamarind kernel seed. Kernel. Yeah, yeah. Okay. No, no. Yeah, it is totally soluble in water because we are. That's why we are using water only, so that it can be removed later on easily with water. Yeah, yeah. It doesn't need water, hot water. Normal. For example, like if you want to test it, for example, I'm pouring this solution in petri dish and drying it. Okay, and after that it's form film. Uh, Instead of peeling it, I just pour some water, cold water. After some time, you will see that film automatically came out because it's hydrophilic anyway. That's the major challenge, because if you want to make something biodegradable, that that must be hydrophilic also. That's why plastic is not biodegradable. That's very hydrophobic. Hydrophobic. Oxo. No, we haven't performed. We haven't performed. We are just doing this look as a soil burial method. This is disintegration of the film, not degradation. Disintegration we are doing only. Cannot say. Like piercing, it cannot say that much. If you have to do like twice, coating twice, then only it will give some significant effect. Otherwise, it will only save the bruising, and that in transportation, like for example, in transportation, cases is going. So there are some like bumps is coming, so it will save the bruising, and it will reduce this damages, like getting softened in the one end, not hard in the other end.